She's a PhD student at MIT, and she's working with Dr. David Sontag and Peter Solowitz. And her main research focuses on building machine learning methods to advance healthcare and fairness. And today, one of the topics she's presenting, it's one of her recent papers in NIPS. And yeah, I guess you can take it.
All right, thank you so much. Let me figure out, should I clip this to me? All right. Oh, great. Okay, it all works. Hi, my name is Irene. Thank you so much for the great introduction. It's great to be here on a snowy, picturesque day. I actually drove in from Boston this morning, and I was a little worried about the road conditions, but I'm happy to report that I made it and that it's beautiful, so it all works out. As mentioned, I'm going to be talking today about a recent paper we had at NeurIPS in December, and this is joint work with the postdoc Frederick Johansson and my advisor David Sontag. Maybe, oh, yeah. All right, so if you didn't know anything about machine learning and you were only paying attention to the news, you might think that we've actually solved a lot of different areas at this point. So as examples, we can beat dermatologists for classifying skin cancer. We can play Dota better than me, definitely, but better than other people as well. We can sentence people to jail. We can predict if child protective services should be called in for different cases. And as many of you may know, in machine learning, we have a lot of ways to go. But one of the important things right now is that as we start expanding and having impact in different fields, from video games to healthcare, it's important that we start thinking about what the implications of that might be. One of the areas that the field has been very excited and interested in over the last few years is fairness. So we'll define fairness in a little bit, but I want to talk a little bit about considerations and what fairness means broadly. So one of the very specific things is that fairness might change by different domains. So it may refer in healthcare, it might mean something different, and criminal justice might mean something different, but essentially we're talking about a broad ethical question of how to assess performance across different populations. So how does a model trained on one population perform on another population? How does a model trained on the whole population perform on one subset compared to another subset? Because we're in the real world on real applications, we're working with real data as well. This data could be historically biased, meaning that decisions made by humans could be biased, and now we're training on that biased data. It could be unbalanced by groups. So I am Asian American. According to the last census, Asians are 5% of the US population. It's pretty small, and it could be incomplete. Because my lab works mainly in healthcare, all of my anecdotes will be about healthcare, but historically we've observed that different racial groups are less likely to seek healthcare at different rates because of historical injustices. And so the goal of my research then is to figure out how to empower machine learning researchers. So people like you to go out and figure out a way to help problems. Some of the approaches that we've tried are then data collection, so figuring out where exactly we should go get more data, how could we proactively audit, and then also, if there's a human in the loop, does that solve everything, or is the human kind of not perfect either, and how do we take that into account as well? So today, I'm going to be talking about a paper that does not address all of these, but addresses some. Specifically, how can we assess across different populations, especially if it's unbiased by groups, and then also inform targeted data collection moving forward. All right. Here's a summary of the talk. So essentially, we're looking to identify sources of unfairness. If we find that a model is unfair, why? What is going on? What might explain this phenomenon? The hope, then, is that we could use this to direct resources. In our paper, we decompose unfairness into bias, variance, and noise, which are 3 machine learning terms that introductory students might have heard of. And then lastly, we demonstrate the effectiveness of 2 techniques. One is feature augmentation, so collecting more features. And then the second one is training data collection, so how to add more training data. All right. The motivation of this problem, as I explained earlier, my lab works in clinical healthcare. When I was a first-year PhD student, one of my first projects was to take clinical notes collected in the ICU, the intensive care unit, and to predict who is going to die in the intensive care unit. The hope is that if we have better predictors, we can help clinicians make better decisions in the intensive care unit. Imagine my surprise then when I found that different groups had different accuracies for the same predictor. So we could imagine that there's a yellow group, group A, and blue group, group B, and we are measuring the error rate. So higher is worse here. And what we found is that for some groups, they have much higher error than other groups. So for example, here the blue group B has higher error than the yellow group A. And we might call that difference the disparate impact of the algorithm. This is something that we are concerned about. In a perfect world, maybe all of them would be the same error. What's going on? Why would there be such error? And specifically, how could we quantify the different sources of that error? For example, what if the blue group is much smaller than the yellow group? So what if there's only like 5 blue people, and because there's so few of them, we weren't able to learn a comprehensive model for those blue people? Then, when we compare against the yellow group, which could have an order of magnitude more people, we aren't able to learn as effectively for the blue people. This would be an example of differing sample sizes, so variance, impacting the unfairness. Likely, we have feature selection. So what if there is a lab test that would really help the blue group out there, but we don't do that lab test because it's too expensive, or because the group, we don't know that yet. For whatever reason, we're not collecting the right feature that could unlock this added accuracy for the blue group. And then lastly, model class fit. The simplest way I like to think about this is if one group is a linear model and the other group is fit by a nonlinear model, restricting our model class to only linear models then would impact the end sources of unfairness. And we'll talk about that a little bit in depth. So that's at a high level where we talk what I mean when I say sources of unfairness. It's important to take a step back, though, and acknowledge that there's been a lot of prior work in classification fairness. So at the time when I started looking at this project, this is sort of the list of references that I started looking at, and then while I was writing this paper and while I was doing all this research, this list probably quadrupled. But this is only a subset of the approaches towards fairness out there. There's been a lot of work on loss function constraints. So if you say, hey, you need to be fair you're trying to minimize this loss, which includes fairness and accuracy, how could you go about that? There's representation learning, where you learn a representation that loses information about the group, and then, but while still trying to maximize accuracy. There's regularization techniques, and then most interestingly, there's a lot of trade-off work. So between different definitions, how could we have multiple definitions of fairness, and maybe it's impossible to satisfy too many definitions at the exact same time. The problem with a lot of this work, or not the problem necessarily, but one thing to keep in mind for these works is that they mainly revolve around the model. They say you have fixed data, and we want to make a model even better given our fixed data. But that's not actually how things work, as I explained earlier. So other things about the data might impact the whole classification fairness framework. So things like the data preprocessing, which there's been some work on as well. Which cohort that you're selecting. Are you only looking at people who have come to the ICU in the last 2 years? Are you looking at the last 10 years? What kind of sample sizes, what kind of features, what kind of group distributions? These are all important factors. And so, which led our work to conclude that we should examine fairness algorithms then in the context of both the data and the model. So let's walk through a little bit why classifier might be unfair in the first place. I briefly alluded to it, but sometimes visually it's easier to walk through. So let's say we have some blue dots and some orange dots. As you can see, there's a lot few orange dots, but we want to fit a classifier to the data set. They come from an underlying true data distribution, but we don't know that yet. We could fit a learned model to one of them, or we could use actually the group variable as a feature, and we could fit 2 separate models. But either way we slice it, because of the true data distribution, our average error for the orange dots will be higher than the average error from the blue dots. And that's because of how few orange dots there are. Therefore, when we do unfairness as, say, the difference between accuracies, we'll see that they'll have larger errors for the orange dots than the blue dots, and we'll have more unfairness for the orange dots than the blue dots. So yeah, so we would call that variance, and we would recommend collecting more samples as a result. We might also have a situation where we have the exact same number of dots. I made this slide, so I know I counted. There are exactly 23 dots on each group. Again, we could learn one model. We could learn two models. But again, we'll find that the average orange dot error is going to be higher than the average blue dot error. In this case, it's a little more subtle, but it turns out that the orange dots come from a quadratic data generating function, and the blue dots come from a linear data generating function. Therefore, no matter what linear function we fit, the orange dots will still suffer. They'll have higher error than the blue dots. So we call this bias. This is changing the model class, which might also include hyperparameter tuning. And lastly, here we have orange dots, blue dots again. Again, I made this slide, so I know they're exactly the same number of dots. I know, also because I made the slide, I know they're both linear. But when we fit a line, and actually I know that the data generating functions are right on top of each other, we find that the average error for the orange dots is still higher than the average error for the blue dots. And this is because just kidding. All right, the amount of error, the noise is different for the two groups. So even though the true data generating function, we're getting very close to it, the noise that impacts the value of the orange dots is higher, and it's harder to measure that. So I think I'm missing a slide here, but you could imagine that it says noise, and that's you should collect more features as a result. Getting a little bit more mathy here, let's say we have X, which is our input, Y, which is our output, and A, which is our sensitive group. So we could think of this as race, gender, socioeconomic status, handicap status, any kind of what part of the country you're from, any sort of sensitive group that we're considering. We know that the group might impact X, and the group might impact Y. But for here, we're going to assume that this connection is very weak. On below, we've graphed the two data densities for the red group and the blue group. So A equals 1 and A equals 0, and we see that they're not overlapping. And also, we've graphed probability of Y given X and how much noise there'll be. If we assume that they're all binary variables, and we are trying to do, we want to predict Y from X, then if we have a high noise rate, so if we have something closer to 0.5, it'll be really hard to reconstruct what X was given Y. And then again, because the red line, because of the red group is in a regime with higher noise, we might expect then that the red group will have higher noise than the blue group will have lower noise. I'm going to pause here to see if anyone has any questions, because sometimes you'll have questions here. Okay, so this is the difference between noises. Here we have, again, very similar. The two densities are on top of each other now. So the probability of X given A for both groups are very, very similar. However, we still have an uneven noise function depending on which regime we're in. Here, any difference between the two groups is now caused by the number of samples drawn from each group. If one group has much fewer samples, we could imagine that they'll fall in some regime that's either very high noise over here or very low noise over here. And that might cause then the differences between the two accuracies to vary. Yes, and then also because these two densities are almost right on top of each other, we've made this a dotted line to indicate that the distribution of X and Y is the impact of A on X is very weak. All right, last, this is explaining bias. So here we have, again, X and Y, red group, blue group, A equals 1, A equals 0. And again, we have some sort of P of Y given X, but unlike last time, it's not very smooth. It's actually this piecewise bumpy function here. Because of our model class is Y hat here, which looks like something like a sigmoid, it's actually not very well approximating this function at all. But that's the model class that we have. Additionally, it does really well approximate over here because this is flat and the green line is also flat. But here it's very bumpy, while the green line is very smooth. Therefore, the red group will have a lot of error compared to the blue group, which is in an area where it's much smoother. This is an example of how model fit might not be very good for one group compared to the other group because of the different distributions of the data. All right, any questions here? This is good to build intuition, especially about bias, variance, and noise. Yes?
So I'm probably jumping ahead of
Okay.
you, so feel free to
No worries.
But is the solution then to treat groups separately and train different classifiers and that?
That's an excellent question because we don't address that later. So in our experiments, when we ran it, that doesn't lead to better accuracy using as a group because people are people and the data points are all relatively similar. And although there are these differences in error, training them separately will actually lead to decrease in accuracy for both groups. Although I can imagine it. Right. Yeah. Since there's some overlap here, having one big model is more helpful, but you could imagine if they're so different, you're classifying cats and dogs, you might as well just have different cat model and different dog model. But that's a good question. Other thoughts? If you're confused, I can go back and explain any of these slides. All right, but we'll move on. So I've been talking loosely about fairness at this point, so let's go ahead and formalize what I mean by that. Here we talk about fairness in the context of loss. This is drawing on probably the last 4 years of fairness literature is really about defining it in terms of loss values, although there are many other definitions that we can also talk about. Grab me after the talk. But here we talk about false positive rates, false negative rates, and a 0-1 loss. And we're mainly concerned with, for some data D and some prediction Y, so a function that we've already trained, what is this little gamma for some group? Little gamma A for some group could be the 0-1 loss for group A over this data set. Then, when we look at unfairness, we're concerned with the group differences. So we might accept that we can't have them be completely equal, so we want to get the differences between the two errors to be as small as possible. So the differences between the two 0-1 losses for the yellow group and the blue group should be very, very small, probably close to 0, but still positive for all kinds of other reasons. Yes. Prior work that precedes me, particularly Pedro Domingos in 2000, had a paper at ICML where he looked at decomposing accuracy into bias, variance, and noise. So in this context, for a single classifier, can you decompose into bias, variance, and noise, and what that might look like? So he took basically 20 years of prior papers looking at these things, stuck them all into one paper. It's a pretty good read. I would highly recommend it. But essentially, once we get, nope, that's not how you use this. Okay, once we get some, the bar here signifies over some sample. Once we have the 0-1 loss for some sample, we could decompose into bias for that sample, variance for the sample, and noise for that sample. And then, because of this difference, because we've defined big gamma, the unfairness, as the difference between two errors, and because we defined the error as bias, variance plus noise, bias plus variance plus noise, we could then define big gamma, the unfairness, as the absolute value of the difference between bias, the difference between variance, and the difference between noise. All right. I want to take a little, I think we should all just stare at this for a little second. And I'm going to point out a few things. So this is main crux of the paper. This is theorem 1, and this is what drives a lot of the experiments. So I mean, I'd happily spend a lot more time here, but I want to make sure that we all get the gist here. Essentially, what we're looking at then is that the unfairness is some combination of these differences of factors. So one thing I'll go ahead and point out is that there's no absolute value in between each of these terms. So we could have one group that has much higher variance, but much lower noise comparatively, and it all kind of evens out. That's something that we were able to show in synthetic experiments, but that is sort of how, so you can imagine maybe you're born to very rich parents, but then you had a bunch of bad luck in your life, and it sort of evens out, and you're sort of the same. Another question is what happens if the noises don't equal each other? Because noise is not a function of the model or the data, it is if the data generating function has really different noises for the two groups, it is impossible to get zero unfairness without increasing bias or variance for the other two groups. In that case, we would not expect to have unfairness be zero because the noises are different and nothing else. It's very hard to, it is not possible to get zero unfairness then without increasing bias or variance for the other two groups. And then realistically, how would we even estimate these samples? Bias is, okay, I'll start with variance. Variance is the easiest. Variance, we can change the different sample sizes and see the effects. I'll formalize that in a second. And then if we did that, we could get both variance 1 and variance 2. Bias and noise are a little harder to estimate. Bias, we can start to experiment with different model classes. The problem is that we have different hyperparameter settings, different optimization techniques, and we might not even come to the global maximum or minimum depending on your loss function. At that point, and also now that we already can handle variance, how do we get bias and noise how do we separate what is bias and what is noise? One technique that we've just looked into is identifying where we can identify noise. So identifying where we could add more features and then running experiments there, as well as changing the model class. All right, any questions about this slide? Yes?
Is it possible that these states are related for both populations?
So the question is there a dependency on for the two populations?
Suppose the bias is high for one population, it's also high. It creates a model where globally it's wrong for something.
It's possible that they're related because humans are humans and they have underlying things besides they're just the same group. We have seen both cases. So cases where for the two groups they're very different because of the underlying things that impact these data points. Also cases where they're almost the same. So I don't know if I have an answer about when it would and would not correlate. Yes?
This is sample unfairness, right?
Yes.
True expected unfairness. Do you think, what is the interplay between the fact that the models you're fitting are they based on the same sample?
Yeah, so the model, I should be clear about this. So we have a whole data set, we fit it to the whole data set, and then our unfairness, or the little gammas, are the conditional accuracies for the specific groups on the same data set. Or it's on a test data, so it's like the same distribution. We'll talk about that in a second. So it's it's test error.
So there's a held out piece of the
Yes,
data set.
yes.
Okay, never mind.
Okay, great. No, you're just brushing your hair. If you have a question, let me know. All right, I'll move on from here. Limitations. So this brings me right into limitations. When does this actually work and not necessarily work? One problem is that we assume that the Ys are fair. So what do I mean by this? A lot of times we are concerned about biased data. What if the thing we're learning on in the first place is kind of a mess? Is it garbage in, garbage out? Here, we assume that the Ys are fine. The X's could be a mess, and that comes out in the noise term, but the Ys should probably be fine. In clinical healthcare, usually who lives and dies does not depend on your group. There are exceptions to this. I can point you to several citations, but usually, and for this purpose, we assume that the Ys are fair. A counterexample then is that in, for example, policing records, it's shown that who gets arrested may be a factor of your race, and therefore if you trained on who got arrested, for all kinds of historical reasons, we might not trust that those labels are as accurate. So that is an important limitation that we acknowledge up front. The second limitation is that later on we're going to recommend gathering additional data. When we say gather additional data, it is not always easy to gather additional data from the same distribution. But through a lot of machine learning, we assume that we can access more data from the same distribution because it is convenient and sometimes true. So for here, we have an example, which is that if you had a clinician and you wanted to label patients from their x-rays, maybe you didn't have enough money to pay the clinician for so many hours, so you said, just give me 200 patients. Now you need more data to make it more fair, so you said, all right, I'll pony up. I'll pay you for another 200 patients, and now we'll have 400 patients total. counterexample, though, is if you have exhausted all of the data from your sources and you wanted to supplement it with another data set distribution, we have no guarantees at this moment about what that would mean. So an example here would be if you wanted to do facial recognition, you're using people's headshots, maybe from a resume data set or whatever, of a headshot data set. If you ran out of headshots and you wanted to use tagged Facebook photos instead, I don't know what your tagged Facebook photos look like, but mine are very different from my headshots, and that would be very different and actually complicate the model entirely. All right, questions about the limitations? Yes?
When you say I have a question about interpretation. When you say data labels y are fair, does that mean they are accurate, or does that mean that py given a is like when you have initial model right a x and
Yes.
y given a
Okay.
y is independent of?
It could be both. So the wording of this implies that py is the true, so that y is actually what happened. But what I mean by fair is py given a equals 1. It's not that the py of a equals 1 is equal to 0. The py of a equals 0. I don't mean that, because that would just mean the rates are the same. But I mean that they are not additional. How do I say this? There is not additional, that the y's are caused by the a's. There's no, the p of y given a equals p of a. Yes. Does that make sense? It's independent. Let me think about, I'll send you something a little more formal. Let me think on that for a second. But yes, verbally, informally, I mean that the labels, these outcomes that we're predicting on in the first place, are not changed by whether or not you are one race or another race. So that would be, okay. Other questions? Cool. So we have two main approaches then. Now that we've decomposed our unfairness into bias, variance, and noise, how would we go about using this? So the one thing I talked about was that variance is actually pretty easy or more straightforward to estimate. The strategy that we use then is by varying the training data, the training set size. Yes. Okay. Previous. All right. Nope. There we go. This one. You can't get more fair by trading. Yes. So we assume this is fixed because we have accuracy on the test set, and we're not messing with that. Yes. Okay. All right. So in order to estimate variance, one method that we came up with then is by varying the training set size. So we have as much training data as we have, and we can't get more at the moment, but we can get less by subsampling. And through that, we can estimate what we call a type 2 learning curve. So if you've taken introductory machine learning, you might have had things where over the number of iterations for like a neural network size or something, you print out the performance over every iteration, and you show that the error goes down. That's known as a type 1 learning curve. So the x-axis then is iterations, and the y-axis is called is like performance or some kind. This is a type 2 learning curve, which is as you increase training set size, what is going on the performance is the y-axis, and that measures how much training set size might impact the performance. Both type 1 and type 2 learning curves have been empirically shown to fit inverse power laws. For those who have forgotten what an inverse power law is, we have some term n, which is our independent variable. We have a negative exponent, and we have some coefficients and constants. The nice thing about this now is that 1, it's pretty easy to fit, and 2, we have a constant term outside. So we would take our data set, we would subsample down, and we would plot this curve for the training set size. Then we could fit it using an inverse power law. And taking that, we could actually figure out what our constant term, I think it's delta here, and figure out what is our intercept term. If our intercept term is 0, it says that if we just had infinite data, if we got n and we made it all the way very, very big, then we would have no error left at the end. That this would eventually go to 0 and that more data would solve all of our problems. Note here, though, that because we're comparing the difference between errors, we would actually take this for a equals 1, and then we would have another one for a equals 0, and we would find the difference. So we would actually be interested in the difference between these two delta terms. If the delta 1 minus delta 0 is 0, then we know that variance would solve all of our problems. Yes. Yes. These are just different parameters. This is examples of what an inverse power law is. Oh. One for one group, yes. And so we could imagine here we look at this group and we look at this group. Are they going to eventually go to the same intercept or not? And if they go to the same intercept, it doesn't have to be 0, but if it's the same intercept, then for large n, the difference in unfairness is 0. But if it doesn't, then we have some residual unfairness still. If we have residual unfairness, so maybe we say have this one and then the other one sort of seems to go for something smaller, then we would know that we have large unfairness even with large n. We have non-zero unfairness with infinite data. Then we know it's probably from bias or noise. So then approach number 2 that we had was then measuring additional variables. So as I mentioned earlier, if the noise from the two groups, if the noise from the two groups, 0 and 1, no model can be zero discriminatory, so it can't have zero unfairness without additional information or additional bias or variance. So how can we measure when additional variables would be helpful? We came up with 2 techniques, mainly involving clustering. So we could figure out where the difference in error is especially high, which clusters in our data are especially high differences in error, and then get a domain expert to look at that group and say, oh, it's because that group is cancer patients. And that's why, for some reason, cancer patients have very high differences in error, and maybe we should get a blood test or something like that in order to assess more information there. So clustering techniques, I'm not going to go over all of it, but it could include k-means or topic modeling. All right, questions? Great. So the running example that I've done this whole time is mortality prediction for MIMIC 3 clinical notes. MIMIC 3 is an open data set for clinical data, notes, labs, vital signs, all of it in the intensive care unit. And it's a pretty important data set for machine learning and healthcare research in general. Most importantly, it's an open data set, so if anyone wants to reproduce these results, they can, and the code is available online. When I ran my L1 regularized logistic regression, the first thing I found is that there are differences between the racial groups. So in MIMIC, there's 5 self-identified racial groups: Asian, Black, Hispanic, Other, and White. And when you look at those groups, you do the conditional accuracies. You could, and using using statistical significance, specifically a Tukey range test for the pairs to see if they're statistically significant. With very, 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 very small p-value, they are statistically significant. And specifically, we have the confidence intervals here, which you can see are not overlapping. Some overlap, but the null hypothesis is that they're all the same distribution, and they're not. So we found statistically significant racial differences in 0-1 loss. As I mentioned earlier, we can subsample and fit inverse power laws. And as it turns out, I didn't plot the intercepts here, but you can kind of see that they're not going to go all to the same intercept. So in more data, although helpful, as you can see, the errors do go down with more data. The differences in error still remain pretty big. And so then the last thing we did was using topic modeling, we could identify the subpopulations. So 2 examples of topics where we found very high differences. We trained 100 topics on MIMIC using an LDA, using actually Mallet, which is created here. We found 2 topics which we gave to a clinician to label, and he said this one is cancer and this one is cardiac patients. And we were able to show for cancer, the Hispanic error is very low compared to other and even Black patients. And then in the cardiac patients, the other error is very high, the white error is very high, but some of the other groups are relatively smaller. And then the numbers just represent how many patients are in each of these buckets. Questions? Great. Another experiment that we ran is on the UCI Adult data set. So this is the open data set on census records from the 60s, I want to say, where it has people's education and their level, household number in the household, all these other variables, and you want to predict what their income will be. Here we looked at other loss functions. So instead of 0-1 loss, which was also significant, how would false positive and false negative rate change? The y-axis is the difference in accuracy, so we want it to be 0. And we showed that as we have more data, they both go down. This is in a log-log scale, so they do follow an inverse power law here, but because it's log-log, it looks linear, and they both go down pretty far. And we can fit them using the inverse power laws, so we know where it would go. And then lastly, because all this data is categorical, most of it is categorical. There are a few continuous features, and it's not clinical text anymore. It's just data. We can use a lot of Bayes error estimation terms in order to get upper and lower bounds for the noise. So this is another way of computing how much noise we think each group would have. And here we show that, let's see. So it turns out that the men have higher noise than the women. It's actually, in this data set, the women were more accurately classified as their income, and the men had higher error. And so here we show that the noise bounds are higher, lower and upper bounded for the men than the women, depending on different error estimation techniques. Okay. Questions before I sort of wrap up and then take questions? Yes?
So let's say what we're seeing is even when the data is same for different races,
Mm-hmm.
it can happen that the accuracy for one race is better than the accuracy of the other race. Can we do something where we do weighted accuracy for different groups? And let's say we incentivize the model when the model predicts wrong for one ethnic group. Does that make it just overfit the model and it's not fair enough?
So your question is, what happens if we modify the loss function to weight for the different groups? That's one approach. I haven't personally worked that closely with that, and I don't think I ran it on either of these data sets, but I've seen that approach. My concern is that then we're not, so you would want to inverse weight it by the group population or something like that?
Yeah, according to the distribution, you can just define their weights inversely to that. So if the distribution is 3:5, you give the inverse. So you incentivize the model more for one.
Yeah, that's interesting. I haven't thought much about that, but that could work, potentially. Okay, other questions? Cool. Oh, that's backwards. All right, so that was a very fun walkthrough of the paper. I encourage you to read the actual paper, but now you've seen all the figures, so you're probably up to speed. But I also want to pose maybe 5 different things about what potential next directions might be. If you're not working directly in fairness, you can still kind of think about these in the back of your head, and maybe one day you'll end up in fairness as well. So one is, how do we define fairness? The 2 examples I used were clinical and sort of more population income based. It is entirely possible that we will come up with different definitions of fairness for different applications. For example, in the criminal justice system, we really care about whether or not they are absolutely the same, maybe accuracies, false positive rates, false negative rates, all of that. Whereas in the healthcare system, we'd like a really accurate model, and maybe the fairness is not as important because you can't get sued over it in the way that you can get sued in the criminal justice system. Something to think about, and there's definitely different incentive structures in place there. The second one is, how do we certify fairness? A lot of people spend a lot of time working on fairness models that then plug into a larger network of decisions. Right now, we don't have any results about what happens if you take a fair model and you take that output and you have another fair model and take that output and you combine the 2 outputs. Is that still fair? Do 2 fair models together equal a third fair model? And I've certainly seen contradictions where that does not hold, that 2 fair models together might create another unfair model, and then we're back at square one. So how would we change compositional fairness? How would we chain together fairness methods, given that we've put so much work into creating one fairness method? Auditing a model. So everyone loves building machine learning models. no one loves auditing models. How could we make the process of auditing a model more straightforward, more easy for someone who maybe doesn't think about fairness all day to plug in their model and be able to churn out some stats about whether or not the model is fair, under what definitions, and then maybe what steps you could do to fix that model. Protected groups. So here I loosely talked about protected groups as race for a while and then gender as a while. I listed a few other protected groups, but they could be very different things depending on the problem. And also we might not know which protected group they are. In the data set, we explicitly ask, but in other data sets, maybe they forgot to ask for race, maybe they forgot to ask for gender, and we want to make sure that that is still being observed even though we don't observe it directly. There's been some interesting work about intersectionality. So if it's fair by gender and it's fair by race, but then when you do race and gender, it's not fair for a specific subset, that might also be problematic. And then lastly, there's a lot of thinking about what happens over time. So if we work in one regime where we work really hard and we get it fair and we make some decisions based off that, is it possible that later on our model would become unfair for entirely different reasons because of the decisions and the changes that we made in the first model? How do we guarantee that the downstream effects, that if we shifted data sets, anything, as things change, how would our fairness model be able to adapt? All right, and so this is a quick recap. I claim that we want machine learning algorithms that are accurate and fair. I also claim that the model and the data should both be considered. And then hopefully, if you ever think about doing anything related to fairness, you think about using some pretty easy to implement fairness checks that use bias, variance, and noise in order to increase fairness down the road. I think we have some time for questions, but thank you guys.